they have done very, very useful work for us. One person I need to mention is Professor Graves in 1920s, and he proposed energy criteria. So energy criteria. So here is the energy criteria. This is the G, okay? This is G, and G equals for this is, look at this one. For infinite, this is a plate with a hole with a through thickness crack. This is we will not call it a hole, crack, a very, very sharp crack. So we have sigma. Suppose we have the remote the stress sigma, and we also know this is a crack length 2a. And one thing I want to emphasize is that for the central crack, and we always denote the whole length as 2a. And for the edge crack, the whole length we use a single a. Right. So this is very, very important. The thickness is a b here. The thickness of this plate is a b. So this energy method. They use this equation and to calculate this G, and G is called energy release rate. So this is this method is from the perspective of energy release rate. So this equals pi. Pi is a constant, and sigma is sigma. Okay, so this is applied stress, and A is a crack length, and E is Young's modulus, and they compare this G and with this is a GC, and GC is a material resistance to fracture. It is a mechanical property, material resistance to fracture. It is the material property. Okay, if this material is selected, and so this guy's material resistance to fracture is almost fixed. And so this is this energy may include the surface energy, plastic work, and other types of energy dissipation associated with the cracking, propagating crack. I told you guys, if you want to crack some components, you need to apply the energy, right? So this energy, and so energy, this is a balance equilibrium. So the energy, if energy is too high, and so this is the component will crack. This crack when this is a component cracks, some energy and will be released. So this is on how the crack initiates and propagates from the perspective of energy. And so G is, as I said, G is called energy release rate, and so it is a driving force for fracture. Okay, so if this G is equal to GC, that means at this point, this is a critical point. Okay. However, if this G is a little bit higher than the GC, and C means critical, the G is higher than the GC, and so this crack will propagate. So here, if G is greater than GC, crack is going to grow. So how to calculate this GC? And GC is determined using this equation. This guy has a similar form as this is as how we calculate energy release rate. And pi AF A square AC E Young's modulus. AF is a failure stress, at which point, at the stress, at which point, what stress this crack is going to fail. And this AC is a critical, this crack size. And so this GC should be independent of the size and the geometry of the cracked body. So this is our assumption, okay? But sometimes it is not the case. This GC sometimes is dependent upon the geometry and the size of the cracked body. But this is our assumption. Our assumption is that for all the material, okay, for all the same material, and regardless of the geometry and the size of this is a cracked body, and the GC remains the same. Actually, sometimes in reality it's not the case, but in our course, we just assume and GC remains the constant for all the same material, regardless of the size and geometry of the cracked body, right? And so this is so one thing was we will see this diagram a lot and during this course. So this is infinite. This is infinite plate. Actually, in theory we have infinite plate, but practically speaking, we do not have infinite plate, right? How can we have a infinite plate? No, we cannot have. So we just say that the width, the B. No, I'm sorry. The width 60. The width is much larger than this is a crack length, and then we can say, and this is a plate is an infinite plate, right? So I need to let you know, guys. So here is from the perspective of this is energy, and then there is another way to solve the problem using fracture mechanics approach. Another one is based on the stress intensity factor K. Okay, as I told you guys, we have three the crack modes. One is opening, and one is sliding, one is tearing. Right. So this is three different modes. And for these, so how can we how this stress intensity factor is used? And suppose here, look at this diagram. And we have a crack, okay? This is a sharp crack, not as big as this one, it's a very sharp crack. So this is a crack tip, and then we establish XY coordinate the system, and this is 2D, okay, on the screen. So here is a point, okay? So this is a point of interest. And then here, this crack tip is treated as origin, and we connect this origin and this point of interest. So here, okay, so here this line segment forms angle with this x-axis, and which is theta, and also there is r. The distance between the point of interest to the origin is r, right? So this is so for the linear elastic material, and the stresses, all the stresses near the tip of the crack, and can be written in terms of this equation, right? In terms of this equation, and sigma ij equals ki. Ki is a stress intensity factor for model 1, and square root 2 pi r. R is the distance between the point of interest and to this origin. And so this ij theta, this is a function, and this guy is a function of the theta, and which is angle formed by the x-axis and the line between the point of interest and to this origin. So sigma ij, and if you have learned this mechanical solids, sigma ij, I from 1 to 3, and j from 1 to 3, and this is sigma ij covers all these 6 stress components, right? And so at the textbook, you can look at the textbook, and for different stress component, we have different Fij, the form. And so you need to look at that equation, okay? Equations. So based on the stress intensity factor, and so this Ki, we compare the Ki, right? And this Ki is calculated and based on the geometry, based on the crack size, and based on the applied load. And the KIC, the C stands for the critical. And KIC is a measurement of material resistance. And we compare Ki with KIC. If this equation holds, and we say, and this is a cracked body is in a critical state. So if this Ki a little bit high, and the crack and is going to grow, right? So this Ki we call the driving force for the fracture, and KIC, and we say this guy is material property. So the same as GC, we also think this KIC is dependent upon the geometry and the crack size, the size of the cracked body, right? And so you can see that, and for this Ki, and which is a constant, and this guy completely characterizes can characterize the crack tip conditions in a linear elastic material. And first, you need to know that this is only for linear elastic material. We also assume the KIC is a size-dependent material property of the cracked body. And so actually, so that this G and the Ki, and there is an equation, and which beautifully and which beautifully connects them together. So this G equals Ki squared over E. And you should also know that this equation only holds for this is a linear elastic material. Okay? And a G approach and K approach, they are equivalent and for linear elastic material. So these two approaches are equivalent, are interchangeable. So any questions so far? And for the G, and for this Ki, and GC, and for KIC. So fraction mechanics often plays a very, very important role in the prediction of components that are subject to time-dependent crack growth mechanisms. For example, the fatigue or stress corrosion cracking. So if you have taken the machine design with me and you are familiar, I think you are familiar with this equation, okay? This is called the Paris, called the Paris law. And this is fatigue, and for the fatigue. And A is a crack length, and N is the number of cycles, and C and M, and they are material properties, and different materials, they have different C and different M values. And delta K is a stress intensity factor range. And so this is a fatigue. Fatigue means that cyclic loading is applied, right? For maximum load, and we have this K maximum at the tip for this crack. If we use the minimum load, we have this is K minimum. So K maximum and K minimum, and the difference between these two guys gives us the range of the K. So which is denoted as delta K. So this equation can be rearranged a little bit. So we just dA here and put this dA and to the right hand side and put all these guys and to this left hand side, right? So this then we take the then integrate on both sides. So then N is number of cycles and to failure, and this guy equals integration over the integration dN, right? So here this guy equals for this left hand side for this equation, I just switch these two sides. So this we have this integration A0 AF and 1 over C delta Km, C delta K power M, and they are located this is denominator for this integrand here. So this is the dA, okay? So A0 is initial crack length, and AF is a finite crack length. So what does that say? Right? It says that if I know the cyclic loading, and then I calculate K maximum and K minimum, if also I know at the very beginning the initial crack length, and I also know when and this we will treat this cracked body and fill so AF. You can define AF, right? This A0, this AF, and from between this A0 and AF, I can calculate if I know A0 and AF, and then I can calculate the number of cycles to failure. So this AF depends on when you think this is a cracked body fails. So this AF, usually we say it yields. If this is the stress, it yields. I had an example for you guys when I taught the machine design. You can just review the lecture notes. And later when we talk about the fatigue life in our fracture mechanics I'm going to give you a similar example to illustrate and how we solve the number of cycles to failure based on this Paris law. So this method, this approach, we call damage tolerance approach. Damage tolerance approach means that I found a crack, but I also initial crack. I know when it will crack, when it will finally the fracture, the fails, and then I can calculate the number of cycles that I can still use my component and to save money. Right? So this is called damage tolerance approach. And second approach I have taught also, and it's called an SN diagram. SN diagram, S stands for stress, and N stands for number of cycles. If you have taken either CAE with me or this is machine design with me, and you should be very familiar with this SN diagram. Any questions so far? Okay. If there's no question, we move on to next one. Next one, I got this one from the textbook. Right? Look at for first, for this picture, and this figure 1.11. So this picture shows us the family tree of fracture mechanics, and it also show us look at here. Okay, for linear elastic fracture mechanics, LEFM. So this is our chapter 2, and we are going to spend a lot of time on it. So this is fundamentals. I hope you guys learn this one very, very well. So you should know that this for linear materials, and also the materials is time independent, right? So second, the topic is elastic plastic fracture mechanics. And this is corresponds to the chapter 3. You should know that for this one, and we will not just take care of the elastic deformation, we also take care of the plastic deformation. And however, and for this one, and still the material is time independent. And for this one, we will say non-linear because there's a plasticity, but still the time independent material. So this chapter 2 and chapter 3, and will be the focus of our the course of this course. So for the higher level, and we will have time dependent material. So this time dependent material is a huge difference. There is a huge difference between time dependent material and from this time independent material, right? So it is more complicated. And for this time dependent material, and we will take care of dynamic fracture mechanics, where we will learn this one. Okay, for linear elastic fracture mechanics, and we will use it also. So look at, you can do that's what it says. But for the LEFM, and we just assume the material is time independent, right? Then we have viscoelastic fracture mechanics, and viscoelastic is more complicated. And this is viscoplastic and fracture mechanics. So the strain rate is very, very important also for this one and for this one because the viscosity. So this is what this picture says. As I told you guys, and we are going to focus on these two chapters and also dynamic fracture mechanics, and we will learn this chapter also, but based on the linear elastic fracture mechanics. So this picture shows us the effect of fracture toughness on the governing failure mechanism. Okay, guys. So look at this one. The fracture toughness. If the fracture toughness is reasonably low, is reasonable. Okay, and so this LEFM can be used. Linear elastic fracture mechanics can be used for brittle fracture. Okay, it means that before the whole body feels the crack initiates and propagates. So as long as the K is bigger than the KIC. Okay, so this is for this one in this region, LEFM and can be used. This is one extreme. Another extreme is the fracture toughness is KIC is very high. Okay, what does that mean? You cannot fracture it. Okay, so this is a problem. If you cannot fracture it, and we will not use LEFM, and we will use limit load analysis. And what is a limit load analysis? Limit load analysis means that, and we want all the points of this, all the material points within this domain to undergo the plastic deformation flow. We want to see the flows, right? So this is another extreme. You understand, guys? Because the KIC is extremely high and you cannot crack it, and then you will see if you keep this increasing the load, and so you are going to, the whole problem domain is going to flow, plastic flow, right? So this is another extreme. And between these two extremes, we can use nonlinear fracture mechanics, either elastic plastic fracture mechanics, and this is for time independent material, or visco-plastic and fracture mechanics. Okay, guys? Any questions so far? Okay, guys. So based on this picture, I wanted you guys to know there are two extremes. One extreme is the KIC is reasonably low, and if we apply some load and some cracks can initiate and propagate. Okay, so then we use LEFM to solve. Another extreme is that the KIC is extremely high, and no matter how you apply the load, you cannot crack the body. And what will be a problem if you keep increasing the load, and all the material finally all the material property, material point is going to flow, plastically flow, right? So if this is the case, and we will use limit load analysis. And if you are going to take fracture plasticity with me next semester, and I'm going to teach you the limit load analysis. Okay, so you can see for this is infinite through thickness, this is central hole, and through thickness. So we can see this is crack length is 2A, right? And then this table shows the typical fracture behavior of selected materials. So for these typical materials, and we have, this is high, for example, high strength steel and linear elastic, right? Linear elastic, and low and medium stress steel, elastic, plastic, fully plastic. And so this table is based on this, okay, guys? So we compare the strength, and this is the toughness. If the ratio of the strength and the toughness, if it depends on, so this depends on the ratio of the toughness, the ratio of the stress to this is the toughness of the material, right? So this is for austenitic stainless steel and fully plastic. And so for the ceramic composites, it is very brittle. This is so linear elastic. For the monolithic ceramics, we have linear elastic. For ceramics at high temperature and viscoplastic. So this table is very useful whenever you want to solve a problem, to analyze a problem material, and you can look at this as a table. One thing I want to remind is that as the time goes, we have a lot of new materials, right? We have a lot of new materials. So this is which these new materials are not included in this table. If this is the case, and you need to do your own research, right? So to see, and what kind of fracture mechanics branch we should use and to solve the problem. Then I'm going to talk about another very important concept, dimensional analysis. Dimensional analysis is very useful. If you want to do some experiments and you want to get some trend data and then train this data, and I hope you guys learn this dimensional analysis very well. So this is a very powerful tool and to do the data analysis and to extract important information, the trend, to transfer the data. So basically speaking, all physical laws are dimensionally homogeneous, right? So are dimensionally homogeneous, all physical laws. So this is Buckingham pi theorem. So this is called theorem is Buckingham pi theorem, and all the same as the dimensional analysis. I'm going to elaborate on what this pi theorem is, how this pi theorem solves the problem to get the relationship between the dependent variable and the multiple independent variables. So for example, we have variables, okay, and variables u, and u is a dependent variable, okay. It's a dependent variable, is a result, and we also have multiple n. This is a dependent variable. They are denoted as w1, w2, and so on and so forth, and wn. So for each of these variables, including this dependent variable and these n independent variables, and each of them has its own dimensions, right? And so their dimensions now are denoted as this square bracket, and this is a variable. For example, this u, this guy's dimension is square brackets u. For this wn, and this guy's dimension is wn. And the dimension means the units, right? So we want to get this information, and u is a function of this w1, w2 through this wn. And we want to get this function. And which independent variables are critical, and we do not know. And now I'm going to show you guys on how to find the most important, the critical, most important these independent variables, and based on the dimensional analysis, right? And first, from all these variables, right? For this, all these is variables, and we have m fundamental dimensional units. They must be fundamental dimensional units. What does that mean? For example, L1, L2, and Lm. So we have so many variables, right? And we know that L1 is in length, L2 is time, L3 is mass. So length, time, mass, and they are fundamental dimensional units. Can somebody tell me another one? Can you? Okay, length, independent, the fundamental variable. Time, independent variable, fundamental variable, dimensional unit. The mass is another independent, the dimensional unit, right? So these are three. So then we identify m private variables that contain all this is the FDUs. So for our case, we have length, time, mass, right? For this one, suppose we have W1, W2, and Wm, and they have 3 primary M. The M, this is the primary, variables. And then this is N minus M, and they are called secondary variables. Okay, guys? And then if I know the primary variables, so all these secondary variables can be written in terms of these primary variables. I'm just talking about the dimensions, unit. I'm not talking about the specific number. You understand, guys? Okay, so you should remember, you should keep this in mind that I'm just talking about the units. I'm not talking about the specific number, okay? So for this primary, if I have selected these primary variables, and then all these secondary variables, their dimensions can be written in terms of dimensions of this is the primary variables, right? So here is the power, this exponent, and this exponent, okay? So this exponent can be 0, can be 1, can be any kind of number. You understand, guys? If this one equals 0, that means, so this guy has nothing to do with W1, right? You should know that. So the third step is that I define new dimensionless the quantities pi j, right? So the pi j, how to define this pi j? And if I have this secondary variable Wm plus j, right? I also know this guy's dimension, and this guy has a number, right? This guy has a number and dimension, and then I divide this guy by the dimension only, then what will happen? And then I will just have a number, that is dimensionless number. You understand, guys? Because the dimension of the numerator and the dimension of because this one, okay, is the dimension of this. You understand? Just as kilogram, if I hear this is a kilogram, and here this guy is a kilogram, and kilogram cancels kilogram, you just have a pure number. So the dimension is. And then this u, and you can dimensionalize, you can make this u dimensionless also. U, right? And u is a variable, is a variable, and this guy divided by its own dimension, and definitely it will be a dimensionless pure number. Do you guys agree? So finally, this equation, so this is equation, which is, so f is to be determined, and change becomes the pi equals f multiplied, this is capital F, okay? So because I just do these manipulations, so definitely on the format of this lowercase f and the format of this capital F and will be different. No doubt, usually they are different. Okay? And if this is the case, so this is pi will be F, and pi 1, pi 2, and it's a pi n minus m. You should know that. So this is for the secondary variable. All the primary variables, they disappear. You understand? They are not disappeared. They just be they have been taken care of by using this dimensionless the process of we just dimension, make them dimensionless. So if n, capital N is greater than m, the function can be determined easily. Okay, guys, any questions so far? Okay, so and then I give you 3 examples how we use the dimensional analysis in fractal mechanics. As I said, so this is a powerful analyzing tool. It's not just useful in the fractal mechanics, and this guy is useful for any kind of data extraction, for any kind of establishment of relationship among these some variables. So I'm going to give 3 examples for in fractal mechanics. Okay, so 3 examples. And first example is infinite plate. As I told you guys, infinite plate is practically it is not infinite. It just means that this guy's width is much larger than the crack length. You should also know that, and this is the crack is not central crack, it is edge crack. For the edge crack, and this is A, okay? For the central crack, the whole length is denoted as 2A. And you should be very, very careful. You should keep this in mind, right? So suppose we have this configuration and we have some load, okay, remote load. So sigma infinity. And so this is sigma infinity. We have the crack length A for any given point of interest here. And so this guy, this is a crack tip. This is a crack tip. And here you have R, the distance between the crack tip and the point of interest is R. The angle between this line and this is x-axis, horizontal axis is theta, okay? So sigma ij near this crack tip and can be written as a function of all these variables. These variables include sigma infinity, definitely this is a externally applied load, and definitely the crack length A, right? And definitely the Young's modulus of this is a cracked body, and also the Poisson's ratio of this cracked body, and definitely, and this sigma value is dependent upon this is how far and the point of interest is away from this crack tip, and also the orientation theta, right, guys? Okay, so let's look at all these variables. I know that and sigma ij, and sigma ij has a variable. What is the dimension this guy has? And this guy's dimension is, I forgot. Can somebody remind me? Sigma ij, this guy is a stress, right? The stress dimension. So sigma infinity, yeah, is a stress. It's stress also. And A is a crack length. Yeah, it's a length, right? So this is the length. These are also the length. The theta, what's the theta? Does theta have radius? Here, theta, theta has no radius. So this theta is dimensionless. Also, the Young's Poisson's ratio is dimensionless also. So then, so this is stress. We have stress dimensions, and we have length, right? And we select these 2 guys as our primary quantities, primary dimensions, and then we will see what will happen. Okay. So for the primary and for the primary quantity, we have this stress, and we have length, right? Then, and this guy we can dimensionalize this one, so make this one dimensionless. So how to do it? Sigma ij divided by sigma infinity. Right, guys? Look at here. I just use a dimension. This is dimension I just created, and this guy is a combination of this primary dimension and this primary dimension, right? And also this one, then this one can be 0, can be 1, can be any number. And for this case, I just make this is A, another second, the primary quantities, the exponent, dimensions exponent equals 0. So that one will take care of, right? So I only have this guy divided by this, and I need to change the format of this function from lowercase f1 and to this is capital F1. So E. So this is sigma. This sigma will be taken, will be thrown away because this guy is primary and A is a primary, right? So all the primary variables will be thrown away. Why? Because they are going to be used to make other quantities dimensionless. So E is here, okay? E has the same dimension of sigma, right? And also, and you can have the sigma. The sigma's dimensions is a power is exponent is 1, and however length exponent is 0. So the length, the influence will be gone, right? So E sigma infinity, and nu, I said nu is dimensionless, right? Dimensionless already. I don't need to take care of it again. Theta is dimensionless again. Dimensionless. I don't need to take care of it again. So this R, for this R, how can I dimension? Make it dimensionless. How can I do that? I'm going to this R, right, divided by the dimension of sigma. But for this sigma, dimension sigma, and this guy's exponent, I just use 0. So this guy has no contribution, right? But for the length, I just use the length, this dimension, this length dimensions exponent as 1. So just R divided by A, right? So finally, so I can get this equation and this equation, F1 needs to be determined. Any questions so far? And how can I determine F1? And you need to use the specific data. You understand, guys? Okay, great. So second example is finite width elastic crack. So this guy is different from this, and because the size of this guy is not infinite, not very huge, the W is reasonable, is a reasonable value. For this one, okay, and we can write this is sigma ij as F2, and the sigma infinity plays a very, very important role, no doubt. A, crack length, Young's modulus of the material. Nu is the Poisson's ratio of the material. R is the distance between the point of interest and to this is the crack tip. And theta is the orientation, is angle between the x, between the horizontal x, between the horizontal axis, and this is the line connected, the line that connects the crack tip and the point of interest, right? So this is same as here, as this is this example. And first, where is my mouse? First example here. So we do the same thing, right? And we know sigma infinity and this A can be primary quantities. And then we divide each of other components, other variables by these two guys dimension. Definitely this exponent for each, for this is a sigma infinity dimension and also A's dimension, right? And you can have sigma ij, sigma infinity over sigma infinity. This guy will be dimensionless. So F2, I know that if I do some manipulation, the format of this function and the format of this function must be different. Usually they are different, right? So this because sigma infinity and A, they are primary quantities and they will be thrown away, right? And where they are, how they take the make an important plays an important role because these two guys are used to make all other variables dimensionless. So E, how to make E dimensionless? I just divide E by the sigma infinity and also the A, but A, I just use this A's power is exponent as 0, so A has no contribution. So E divided by the sigma infinity, nu is the dimension is itself, you don't need to do anything. R divided by sigma infinity and A, and the exponent of sigma infinity can be selected as 0, so sigma infinity will have no influence. So I will have R over A, and theta is dimensionless already, right? So we don't need to take care of it again. W is width, okay? And width divided by A, but there is no contribution for sigma infinity because we can select the exponent of sigma infinity as 0, and which just neutralize, just void the influence of sigma infinity. Okay, this is our second example. And the third example, and the plasticity is involved. And we have the W, this is finite, the crack, finite width. This guy has finite width. Okay, so we have sigma infinity, we have a crack length, and in front of crack tip, and we have a small plastic zone. And small plastic zone, we know that this guy's radius is Ry. Right? Ry is the radius of this is a plastic circle. So let's establish the relationship between sigma ij and other necessary variables. Sigma ij, I write this guy's function as lowercase f3. So definitely it is dependent upon sigma infinity, crack length, Young's modulus, Poisson's ratio, the distance between the point of interest and to the crack tip, and theta. W is the width of this plate. Ry is the radius of the plastic circle, and sigma y is the yield strength of this material, right? So Ry and sigma y, these two variables, and they are related to the plastic deformation. So, and then we select, we can see, okay, sigma infinity, Young's modulus, sigma y, and these three variables have the dimension of stress. And gamma, and I'm sorry, not gamma, nu, Poisson ratio nu, and theta, and themselves, they are dimensionless themselves. So A, crack length, R is the length, R is the radius, I'm sorry, R is the distance between the point of interest to the crack tip, and Ry is the radius of the plastic circle. So these three variables have the length dimension, right? So then I will have this primary sigma infinity, and this is A, can be treated as the primary variables. As a result, all other variables can be made dimensionless and based on the pi theorem I will just talk about. The result will be sigma ij and sigma infinity equals capital F3 E over sigma infinity E, because these two guys have the same dimension, right? And nu, this guy itself is dimensionless, and no, we don't need to take care of it. R, A, they have the same dimension, and theta is dimensionless itself. WA, and they have the same dimension. Ry and A, they have the same dimension, and sigma y and sigma infinity, and they have the same dimension. So then here, we just make all these variables dimensionless, right? So that's all for today's lecture. I want to recap what we have learned. And we have learned two approaches, fracture mechanics approach. One is energy approach, one is a stress intensity factor approach. And you should know that for the linear elastic materials, and these two approaches are equivalent. They are interchangeable, right? I also talk about the two extremes, how the KIC affects the analysis. And then we talk about dimensional analysis, and we talk about the pi theorem, and you need to know the three-step this procedure, how to use and this procedure and to do the data analysis. And we are going to use this one very, very often in our following lectures. Okay, guys? That's all for today, guys. I hope you have a wonderful afternoon.